This is your title. We're doing 5.6, rational functions. This is going to be today using arrow notation and asymptotes. Introductions to asymptotes. Asymptotes actually has a P in the word. Asymptotes with a P. Asymptotes. Arrow notation and asymptotes. Seth, you're going to miss a good one today.
I'll be here tomorrow.
Okay. Okay, so at the beginning of today's lesson, and actually for the most of today's lesson, there's going to be very little for you to actually have to write down. There's going to be a whole lot of looking and understanding what they're saying. Okay? So, do y'all have all of this? We got a title ready to go? Okay. So, when we say we're talking about rational functions, we're talking about this kind. These are your last two toolkit functions. So up until now, we've covered all of the polynomial functions, right? X squared, x cubed, x to the 1/3, x to the 2/3, or x to the 1/2. We've covered your radical. That would have been the x to the 1/3 and x to the 1/2. Those are the root functions. Y'all are looking at me like I've lost it. We've covered these ones. Y equals x squared. Those are parabolas, right? Y equals x cubed. Those are cubic functions, polynomials like we just talked about. Is this ringing a bell now? Okay. We've done y equals the square root of x, also known as x to the 1/2. Do y'all remember what that guy looks like?
Yeah.
Right? We've done y equals the cubed root of x, or x to the 1/3. What does he look like? A flat S, right? Do y'all remember? Okay, so that's what I'm saying. We've covered all of these already. We've also covered, what else? What other kinds? Absolute value functions, right? Ones that didn't look like a polynomial. They weren't curved or continuous. They had a V. We've covered that kind. Okay, we also covered linear functions. We've dealt with quadratics. This is kind of the last set. These are called rational functions. Rational. And what rational means is fraction. We've got a fraction somewhere in these problems. Okay? Typically, you'll see the first one, this is called the reciprocal function. Reciprocal. Or the second one we call the reciprocal what? Squared. Do y'all remember this one? Y'all remember these from your toolkits? So these pieces are called the branches, the parts of the graphs that you see. They're called the branches. It says several things are apparent if we examine the graph of f of x equals 1 over x. So we're talking about this guy right here, the reciprocal function. On the left branch of the graph, the curve approaches the x-axis as x approaches negative infinity. What that means is as x goes to negative infinity, I'm talking about this branch right here. As x goes to the left, the y value approaches the x-axis. Can you tell that? It approaches the line y equals 0. As x goes to the right, same thing. The function approaches the x-axis, y equals 0. Cool beans? Okay. Another thing happens here. As the graph of x approaches 0, where does f of x go as x approaches 0? Down. How do I say down? Negative infinity. As x approaches 0 from the right, what happens? Positive infinity. Okay? So because it breaks at 0, the function breaks. One tail goes up to infinity, one tail goes down. That's called an asymptote. Okay? More on that later. So we use these arrows, this arrow notation. Okay? When I see this x goes to a with a little minus sign, notice that that doesn't say negative a. I'm talking about right here. This doesn't say negative a. This says a with a minus sign afterwards. The way that reads is x goes to a from the left. Okay? This from the left tells me I'm coming in from the left side. Does that make sense? As x approaches a with a little plus sign out to the side, that tells me I'm approaching a from the right. Does that make sense? Okay, so I'm going to go back to the picture before. This is what I'm saying. So right here, this is I'm approaching 0 from what direction? From which side of 0? This is coming in from the left. Can you tell? Because I'm coming from the left of 0. So the way we would write that is we would say as x approaches 0 from the left. Do you see that? What does f of x do? F of x goes to negative infinity. And if I was going to write it on this side, where am I coming in from?
The right.
From the right. So we would call it the limit as x approaches 0 from the right. X approaches 0 from the right.
Why is it?
We're going to talk about that later today. I'm kind of switching notations on you. So this is kind of baby steps as x approaches, and we write the words s, or as. As we get into big kid land, we're going to start talking in terms of limits. The limit of this function as x approaches 0 from the right is infinity. It's taking this and putting it in math terms. Okay. All right, so let's look at that arrow notation one more time. Yeah, I would probably write down a little bit of this. So just so you know what the little superscripts mean. What does it mean, a to the a with a minus? That means approach from the left. A with a plus is going to mean approach from the right. As x goes to positive infinity, where am I going then? It says increases without bound. Where does that go? Forever to the what? As x approaches infinity, where am I going? As x approaches infinity, to the right. What about as x approaches negative infinity? Where does that go? To the left. F of x approaches infinity. Where does that go? Up. Good. F of x approaches negative infinity. Where does that go? Down. Kind of understanding what these symbols are meaning? The only ones that ought to be confusing to you that you've never seen before are the little a minus and a plus. And all that tells me is from what direction am I approaching this object, this number? Am I coming in from the left? Am I coming in from the right? Okay? Life is good? So on paper, nope, okay. Whoa. Sorry.
I don't know what the output is.
Output's the y values.
Do I need to put those?
No. We know if f of x goes to negative infinity, we're saying the function goes down.
Oh, what about the one below it?
F of x approaches a. We'll look at that today. That means it doesn't necessarily approach negative infinity or positive infinity, but it might ride right along a number somewhere. It's kind of cool. Are y'all good with this? Yes? Okay, so it says local behavior of 1 over x. This is the reciprocal function. It says we cannot divide by 0, right? If I plug in 0 and I have 1 over 0, that function is going to be undefined. But we can determine what the function does as we take x closer and closer and closer to 0. So I want you to look at this table right here. This has x on the top row. Can you see that? I'm talking about this row right here. X on the top row. We're starting at negative 0.1. Then we go negative 0.01. Then it goes negative 0.001. From which direction am I approaching 0 here? From the left, right? These numbers are getting closer and closer to 0, but they're all negative. So what's happening right now is I'm approaching 0 from the left. We could say as x approaches 0 from the left, what's happening with these y values? I'm going to blow them up where you can see them.
They're getting small.
No, smaller in the negative direction, right? So they're getting actually huge, but they're negative. We call that negative infinity. Can you see it? Okay. Right, so the output approaches negative infinity. You see it? Okay. Now, let's switch gears. We're going to approach 0 coming back from the other direction. So we're getting closer and closer and closer to 0 from the right. What happens to the y values? They get bigger. Huge, huge. And so if you can imagine, as x approaches positive infinity, f of x goes to positive infinity. So what's happening here? That means as my function is getting closer and closer to 0, my y values are getting smaller and smaller and smaller. And as my function gets closer and closer to 0 from the right side, my y values get bigger and bigger and bigger. That's why the graph ends up looking like that. Everybody good with it? Okay, so now let's put it all together. Now you can see as x approaches 0 from the right, f of x goes to positive infinity. That's here. As x approaches 0 from the left, f of x goes to negative infinity. That's here. Are you cool with that? This is called local behavior. Local behavior. It's what happens on the insides of the function. What happens on the insides, in the middle. Right? This behavior creates what we call a vertical asymptote. A vertical asymptote, which is a vertical line that the graph approaches but actually never crosses. Okay, it approaches but never crosses. I used to have this little puppy. Her name was Harley, and she was a white lab. You know Labrador retrievers? Anybody ever owned a lab before? They're awful until they turn 2. That's the rule with labs. They make really great dogs. They are horrible puppies. And this dog named Harley ate my yard. Okay, she ate my yard. She ate my sprinkler system. She would pick the pickets off the fence. One day I went in the backyard and I had this shed in the backyard. It had a window in it, a glass window. And the glass window was gone. It wasn't shattered. It wasn't broken. Like there was not evidence of the window. It's just gone. I don't know. But my dad helped me. I was single. I didn't have much money to keep fixing my yard, and I didn't have the heart to get rid of the dog. So he came and helped me, and we put a little hot wire electric fence around the outside of the fence to try to keep her from eating the whole house and the yard, right? So this fence, this boundary, acted like an asymptote for Harley. She knew I can get really close to it, right? But if I ever touch it, and it took her about one time to figure that out. And then you could watch her in the yard, and she would approach it. She would run right up next to that fence. And then as soon as she got close, she would run alongside. And she knew better than to ever cross it again. Okay? That acts like an asymptote here. You can watch the function. It's going to be able to get very, 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 very close, and then it's going to not touch because it knows better. Right? That's an asymptote. Do you understand? Okay, so we wrote down, or we have here, it's a vertical line the graph approaches but never crosses. I would like you to write this. Or maybe you don't even have to write it, okay? I won't make you write it if you can understand what I'm saying. All right? A vertical asymptote of a graph is a vertical line at x equals a, where the graph tends toward positive or negative infinity. Okay, so what happens is if your function ever breaks and the branches tend to go to positive infinity or negative infinity, you're dealing with a vertical asymptote. That's how you know. Because your branches are going to go up and down, around it. They could both go up, and we'll talk about that later. They could both go up, they could both go down. But on either side of the asymptote, if your branch goes to positive or negative infinity, you have an asymptote. Cool? So what is the location of the asymptote, the vertical asymptote in this situation? X equals 0. And so vertical asymptotes are named x equals because they're all vertical lines. X equals the location for where the asymptote actually is. Are we doing okay here? Okay. X equals that number.
Can you put the definition on it?
Yeah, sorry.
It's okay.
X equals. So how do you know it's a vertical asymptote? Because as x approaches that number, f of x goes to positive or negative infinity. As x approaches that number from the right, f of x goes to positive or negative infinity.
Can you turn it a little bit softer right now?
Vertical asymptote. Why was that one at 0? Because on that particular picture, as x approached 0, it went to negative infinity. That's when it happened. The break.
One to the right before it started, that would be like one.
Yep. Yep, and we're going to look at transformations in just a second. Yeah, you're on the right track. Britton, you dying back there? What's wrong? No sleep? No. Y'all had a big old Easter get together. I saw your house was full of people. It was good? Did you have a good weekend? Good. Good. Are we good with this one? Yes? Yes? No? Yes? Okay, on the next page, we're looking at what is called end behavior. And we learned before when we were doing polynomials that end behavior deals with what?
Tails.
The tails. As we go to positive or negative infinity. Okay? Positive or negative infinity. So we're looking at this end or this end. End behavior deals with the tails. Do you see the difference? Local behavior deals with what's happening in the middle of the function. End behavior deals with what happens way out here. Are you following that? Okay. Now, I just told you that an asymptote is a line that a function will approach but never ever cross. And I need to make a distinction. A vertical asymptote will never ever be crossed. A horizontal asymptote could be crossed in the local portions of the function. So on the insides of the function, it could be that it crosses the asymptote every now and then. Horizontal asymptotes deal with the end behavior. So as we go out to the tails, it should approach but never cross. Does that make sense? Okay, so I'm not describing necessarily what's happening on the inner parts of the function when I say an asymptote can never be crossed. Vertical asymptotes will never be crossed. But a horizontal asymptote could be crossed because it deals with what's happening on the end. All right. In calculus, we call this end behavior business limits at infinity. And what that means is you got to get your little Buzz Lightyear helmet on because we're going to infinity and beyond on both sides. Okay? Both ways.
I have a question.
Yeah.
Just 'cause, like, can they be like both on the right or like both on the left?
Oh, would that be?
Wouldn't that be reciprocal squared though?
Okay, so even on reciprocal squared, both would be in the top or both would be in the bottom.
Yeah, that's what I'm saying. Can they both be like on the right or the left?
No, because then it wouldn't be a function. And by definition, a function has to pass the vertical line test, right? So if I had part of my function here and I drew the other part of my function here, that's what you're asking? Doesn't pass a vertical line test. So they'll always be separated such that they're not lined up vertically, stacked. Okay? Great question. A horizontal asymptote. This is new information. A horizontal asymptote is a graph of the line y equals b. Horizontal line y equals b, where the graph approaches the line as the inputs increase or decrease without bound. So when we take our x to infinity or to negative infinity, what does f of x do? Okay, so looking at this reciprocal function, if I take x to positive infinity, this function's going to ride right along this x-axis. Can you tell that? What's the equation for the x-axis? Y equals 0. It's a horizontal line. So that's your horizontal asymptote. You can tell where that's going to be located by taking your x to positive or negative infinity. Okay? So again, if I take this x to x approaches negative infinity, what does f of x do? F of x rides right along that x-axis. It goes to 0. Cool? Y'all want the notes for that horizontal asymptote? A horizontal asymptote of a graph is a horizontal line where the graph approaches as inputs increase or decrease without bound. Notice in this description they don't say it approaches but never touches. They do say that in the vertical. It could, right? What we really say is as we go to infinity, the graph trends toward that line.
So, regardless if it's positive or negative, it's f of x is going to be.
F of x is going to be that number, whatever line it happens to be going to. And we don't necessarily say we're approaching from the left or from the right. Do you know why? Can you approach infinity from the right? Like, can you get on the back side of infinity and come back in? No. There's only one way to approach infinity, and that's from the left. Does that make sense? So I'm not going to have to specify when I'm going to infinity with the little minus or the positive sign. I do have to tell whether I'm going to positive or negative infinity, but I don't have to tell which direction we're approaching from. You can only approach from one direction, right? How do I get to negative infinity? From the right. That's the only way to get there. Are we clear with that? Okay. All right, so let's do example 1 here. Example 1. It says, use arrow notation to describe the end behavior and local behavior of the function graphed in figure 6. So I want you to look at this picture. Fellas, have you ever been like bow hunting? Have you ever used crosshairs and tried to get whatever you were looking at in your crosshairs? So what I imagine here is the crosshairs have moved. Can you see that? So on the parent function, the crosshairs are at y equals 0 and x equals 0. Here, the crosshairs have gone to the right 2 and up 4. Can you see it? Okay, so we're going to use arrow notation. I would write this on your paper. Just draw a really quick sketch. Put a vertical line at at x equals 2. That's your vertical asymptote. Put a horizontal line, a dotted line across at y equals 4. That's your horizontal asymptote. And then fill in the branches. And you don't have to be real specific with the branches. Just put some curves in those quadrants. Just so that we can talk about these arrows. Are we okay? Okay. So let's start. I like to do the tails first, the limits at infinity first. So I'm going to start on this side, on this tail. Okay? The way we write this is we write the limit LIM, and right underneath it you tell of x to what? As x goes to negative infinity. Of f of x equals what? Where does f of x go as we take x to infinity? 4. Good? Okay, now let's do the right side. This is going to be the limit as x goes to what? Positive infinity. Of f of x is 4. Since I got the same number to the right and the left, I can say there is a horizontal asymptote, HA, at, and we name the line, y equals 4. There is a horizontal asymptote at y equals 4.
And are we gonna line up the different?
Yeah. On all the ones that you have in this unit, though, we only have one horizontal asymptote. We don't have to worry about other ones. Cool? Okay, now let's do the other tails. Right? This is going to talk about the local behavior. We're going to do this one as the limit as x approaches what number? 2. And let's specify. This time I'm talking about 2 as I approach from the what direction? Left. Can you tell? I'm coming into 2, but I'm coming in on the left side. Notice that it's not negative 2. It's positive 2 from the left. The negative little sign comes after the 2. Are we cool with that? Of f of x is what? Where does it go? Where does this line go? Negative infinity. Down. Is negative infinity. So the limit as x approaches 2 from the left of f of x is negative infinity. Down. Yeah? Okay, so the limit as x approaches 2 from the right of f of x is positive infinity. And that's how I know I have a vertical asymptote. Because I approached a number, 2, from the left and from the right, and I got two things that went to positive and negative infinity. So there is a vertical asymptote at, vertical asymptotes have x equals equations at x equals 2. How do you feel? Pretty solid? Okay. Do we want to do another one of these, or you want me to leave it alone? Leave it alone? Okay. So I had this one. This was arrow notation to describe the end behavior and local behavior for the reciprocal squared function. I'm going to zoom through it really fast. You don't have to write anything down. But just in case you need it later, I'm going to put it up here. Okay? This would be the function y equals 1 over x squared. And it looks like this. That's a pretty rough sketch. But on the left side, the limit as x approaches negative infinity of f of x is 0. The limit as x approaches positive infinity of f of x is also 0. So there's a horizontal asymptote at y equals 0. Good? If I did the limit as x approaches 0 from the left of f of x, what do I get? Positive infinity. The limit as x approaches 0 from the right, also positive infinity. So I have a vertical asymptote at x equals 0. Good, good? Okay. If you need that one again later, go back and slow it down. I'm sorry. Okay, so I do want to cover this one, though. That's why I skipped ahead. This is example 2. It says sketch the graph of the reciprocal function, so just 1 over x, not 1 over x squared, shifted 2 units to the left and up 3. Okay, so I need you to remember insiders lie, outsiders tell the truth. Outsiders tell the truth. So we're talking about the parent function or the toolkit function, f of x equals 1 over x. We need to shift it to the left 2. So now we have f of x equals 1 over x plus 2. Insiders lie. If I put it with x, I can move it left and right, and it's got to lie. Good? Up 3. Where does that go? Out here. Not inside with x. Outside. All that does is that shifts the crosshairs. So now, instead of my crosshairs being dead center at 0, 0, they're going to be to the left 2 and up 3. With sound effects, it's better. You could make them on your paper. Yep. See? So now, where do I draw it? Up here and down here. So same exact function, it's just scooted. Cool? Now, identify the horizontal and vertical asymptotes. Where is the vertical asymptote? Vertical. X equals -2. And how do you know that? Because as x approached 2 from the left, that's this sign, where did... I got to fix my graph, y'all. I can't live with it. It's making me sad. That's better. As x approached 2, so I have the limit as x approaches 2 from the left of f of x. Where'd it go? Negative infinity. Talking about this tail right here. The limit as x approaches 2 from the left of f of x is negative infinity. -2 from the left. Look at him. That a boy. Approaches -2 from the left. So I got negative signs everywhere. It's a -2 from the left. Good call. And on the other side of that, the limit as x approaches -2 from the right of f of x is positive infinity. Can you tell? Look right here. This tail. It's going up. Positive infinity. Which tells me I've got a vertical asymptote at x equals -2. Cool? Now let's talk these horizontal asymptotes. We're almost done. Don't put up yet. Hey, we're not done yet. How do I write the tail for the left side? The limit something. As negative infinity. Do I have to say from the left or the right? There's only one way to get there. You're coming from the right. Limit as x approaches negative infinity of f of x is 3. Good girl. And talk to me about this tail. The limit of f of x is 3. Good. So, what do we know? There is a horizontal asymptote at y equals 3. Okay. You're going to want to either use Desmos, I would use Desmos, to graph your homework so that you can look at the pictures and you can tell exactly where those asymptotes are. Okay. You're going to have to look at a graph and then tell where the asymptotes are.
Do I have to draw the graphs in?
You don't have to draw them on your homework, but you need to be able to see a picture of them. And that's going to come on Desmos. Whether you do that on your phone or your Chromebook, I don't care. But you got to look at a picture. I wish.
Bring it back in the morning.
I wish.